Hi, kids. How are you? Oh, sorry about my spinning my fan up there. So here's another one where you get to see me while I'm doing my video. So again, I keep meaning to ask, do you prefer it with me on the screen or without me on the screen? I think it's a little weird myself to kind of be looking at this, watching myself teach. Okay, so today's content video is on evaluating limits. Now, I touched a little bit on limits before when we were investigating like the end behavior. I prompted you to use limit language, and I told you not to worry, that we would formalize that a little bit more, and that's what this lesson is about. So looking at graphs, right, which is why in Algebra 2 and Pre-Cal you spend a lot of time studying very familiar functions. Not everything I'm going to give you is familiar, but there should be a lot of graphs that you just kind of have a picture in your head of. If I just say what rational function or exponential function or something like that, that's going to help you evaluate limits graphically. So first, the language, the limit, take it to the limit. I don't know if any of you know who sings that song? Does any song come in? I mean, it is from like the 70s, so let me know if you think of it. All right, so here's the language. The limit as x approaches a number of a function is L. L for limit, L also for level. So as x gets really, 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 really close to a certain number in the domain, your graph gets really, really close to, on both sides, some level. Is that true? What is that level? So that number underneath there is a domain, an x value. The level that you're going to give me is a y description. Right? So I also need you to think about the fact that the limit isn't really a number. The limit is asking you, what behavior do you see on the function around the range values that correspond with values around this domain? So the actual value of the function at that number is irrelevant unless ... We're going to fill in that unless in a minute. So whenever you are actually asked to evaluate a limit, the range value is your default answer. I know that sounds kind of crazy. For example, what is the function behavior? What is the behavior of this function, right, of the range values of this function around x equals 3? Well, because you know what 2x plus 1 looks like, you know it is a continuous function over its domain. If I were to simply ask you to plug in 3, if you just plugged in 3 to the function, what would you get? 7, right? When x is 3, y was 7. Well, look at the range values all around there. If you plugged in 2.9 or 3.1, you wouldn't get 7, but you'd get numbers really, really close to 7, wouldn't you? That's the behavior. So here's a graph, and here are my two range walkers. My range walkers have big bellies. This range walker walks from the left side of the domain, and this range walker walks from the right side of the domain. Okay? And they walk along the range, though. They're range walkers. So as I approach 3 from the left range walker is increasing. As you approach 3 from the right range walker is decreasing. There they are. As x gets closer and closer to 3 from the left and the right, my range walkers meet and their bellies bump. Now you might want to know, why did I have bump? Because where their feet are standing, I want to be clear that their feet are not standing on 7. They're not standing on 3, 7. I really am just plugging in numbers very, very close to 3, but their bellies kind of touch over the limit of 7, right? So the answer to a limit, and you see how L is in red? The answer to a limit might just be the range value. Do you know when that is? When you have something, drum roll, blah, 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 continuity. If your function is continuous, then f of c, this c, is equal to your limit. So that's why it's really nice to know what functions are continuous, because somebody, even if you're not sure what a limit is asking, if you know you have a continuous function, plug and chug, be done. Bumping bellies will always happen. Left range walker, right range walker will always meet and bump their bellies. So the reason I kind of make a big deal about bellies is because look at this example. Here's a function that has a hole. Do you still bump bellies? Right? So let's suppose I still want to know about the limit there's a hole at 3, 7. What if I still want to know what is the limit as x approaches 3 from both sides of this function? What is the behavior of the function not at 3? Function's undefined at 3. So if I asked you for f of 3, the function at 3 is undefined. But what about at 2.99999, 3.00001? Plugging those into the function yields me a cloud, right? Here's my domain cloud, here's my range cloud, and look at my range walkers. Bump! Their feet don't step on the hole, they'd fall through. Ah! Oh no! Right? But their feet aren't on the level of the hole. They're right next to the hole, but their bellies are touching over the hole. Therefore, this level is still 7. Crazy, right? So in this case, the actual value of f of c is irrelevant because I was not continuous at 3. Right? At 3, I wasn't continuous. I would have no issue bumping bellies anywhere else either because the function is continuous everywhere else. So for instance, what if I asked you, what is the limit as x approaches -3? That's right. At -3, this function happens to be -5. Since your function is continuous at -3, the level is -5. Here, the function was not continuous. You had to know the level of the hole, which hopefully is something you were taught how to find algebraically in AAF, right? You remember that. We made you all do it. Okay, so the limit of my function, right, given the graph, right, remember our objective, evaluate limits graphically. Sometimes the graph is just in my head. Y equals 2x plus 1. It's in my head. I don't need to see the graph. This graph I needed to see, the one with the hole in it. The limit as x approaches 3 of the function was 7. Okay, so sometimes the answer to a limit might be the y value of a hole. So think about the little sticky from the previous slide. Sometimes the limit to the answer to a limit problem is actually the function value when you're continuous. Sometimes the answer to a limit value might be the y value of a hole, okay, when you have a point discontinuity. Whoa, hope you remember how to find that. Now, that was a point discontinuity. What about a jump? So here is the greatest integer function, right? We think of this as the round down function. So when you input 1.5, you get a 1 out of that, right? When I input 1.5, round down to the greatest integer that you've already written down, that's a 1. But what about at 2? What happens at x equals 2? As you put in numbers to the greatest integer function, like 1.9 and 1.9 and 1.9999999, you round down to 1, don't you? But what happens when you put in 2.1 and 2.01, 2.00001? You round down to 2. So I forgot to tell you something about my range walkers. Their necks don't bend. They can't see one another, right? They don't meet, they're not at the same level. As I approached 2 from the left side and the right side, as I plugged in 1.99999 and 2.00001, my range values were at different levels. Therefore, since they can't see one another, since there's no bumping bellies, we say the limit does not exist. We don't say undefined. Undefined is for a function value. Remember, the limit is asking for the behavior, and it wants to know, is there a value around, right? When you plug in numbers around the domain, it wants to know if the function behaves the same on both sides. And in this case, the function does not behave the same way on the both sides of 2. It did on both sides of 1.5. If you plugged in 1.5001, you defaulted to 1. You went back to 1. If you entered 1.499999, you rounded down to 1. So the function behavior on both sides of 1.5 was 1. But on both sides of 2, the function behavior was different. So we say the same behavior does not exist, because this implies the same behavior. We call that the overall limit, which means you're looking at both sides. If both sides don't have the same level limit, then the behavior does not exist, meaning the behavior is not the same. But look what happens if I just want to ask you for one side. What's the behavior of the function as you plug in x is really close to 2 from the left, like 1.99 and 1.9999? I only need to know about range walker 1, right? That's all I'm asking for. That level is 1. What about when I ask about the range walker 2? What is the level of range walker 2 as you approach 2 from the right, like 2.01 and 2.0001? That level is 2. Now notice the relationship between the left limit, the left range walker is at a level of 1. The right range walker is at a level of 2. Those are not the same level. Therefore, the overall limit does not exist, right? So what if up here where the overall limit did exist? Do you agree that as you plug in numbers close to 1.5 from the left, like 1.499999, you get 1. So the left range walker is at a level of 1. And the right range walker is at a level of 1. Since the left range walker and the right range walker were at the same level, or the left hand limit is equal to the right hand limit, right? Calculus books don't talk about range walkers, but they do talk about left and right hand. Since they are the same, what is true about the overall limit? The overall limit exists and is at the same level as left range walker, right range walker. I feel a theorem coming on. Okay. So firstly, the answer to a limit might not exist. D and E does not exist. That means there's no bumping bellies. The left-hand range walker and the right-hand range walker do not match. All right, limits with swooshes and slides, okay? Basically vertical and horizontal asymptotes. So let's look at this example. The limit as x approaches 0 from the right of 1 over x. That's supposed to be a function you know. So What is, whoops, sorry. What is the right range walker doing? What is the left range walker doing? Are they doing the same thing? Whoops. Ah. So the graph of 1 over x I didn't give you. You're supposed to know what that looks like. You studied that in Algebra 2. Whoops. You're supposed to know, Ms. Getz. Okay. So I am asking you, this question is, right, since there is a vertical asymptote at x equals 0, I want to know what the function does on the right side of the VA. What does the function do on the left side of the VA? And are those things the same? Now, if I can see the graph in my head, I can see that the range walkers are doing completely opposite things, right? As x approaches 0 from the right, you're plugging in 1 over 0.00000001. Those range values are getting huge, right? And a matter of fact, they don't have a value. That behavior is to positive infinity. So it's a little weird, right, to think about writing equals infinity, because remember, infinity is not a number, but I'm not asking you for a number. Remember, a limit is asking you for behavior. The behavior is to a positive infinity. What about on the left? As you plug in numbers to the left of 0, what's going on? Right? Where's my range walker? Swooshing down to negative infinity. Are those two behaviors the same? I don't think so. So what about the overall limit? The overall limit of a function exists if the left hand and the right hand limit are equal. That's when an overall limit exists. That's a theorem. No one's going to ask you to spit out that theorem, write it down, but you do need to know it. What about this one? Oh, it's not dark enough. See what I did there? You see what I did there? Right? You need to know what that graph looks like. 1 over x squared still has a vertical asymptote and a horizontal asymptote. The right side still looks kind of like this, but you know what the left side does? You're squaring it, so all your range values become, that were negative, become positive, right? So what is the right range walker doing? Hopefully you can see the right range walker is swooshing up. The left range walker is also swooshing up. So does the overall limit exist? Do they bump bellies? Remember, they're not actually, that's why I have the big bellies. They're not actually going to step on where x is equal to 0. They'd fall through the abyss. Who knows where they go? It goes on forever and ever. But both of those range walkers' bellies touch. They get infinitely close to 0 on both sides, right? Without ever actually touching 0. Crazy. So what do you think about this one? Right? This is one, I want you to think about this. This is one that we will do in our live session together. The actual definition of a vertical asymptote involves limits, right and left-hand limits, to an infinity. You don't have to memorize that definition, but you need to conceptually understand it. Vertical asymptotes of rational functions are limits to a number with a positive or negative infinity as an answer. Okay, so vertical asymptotes on rational functions mean swoosh, 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 swoosh. or swoosh whoosh. Now, how about slides? What's the end behavior of the following functions is something I asked you in Algebra 2, right? So this is a rational function. And I said, hey, bottom heavy, since you look at the highest, right? I don't care about this. As I'm going to positive and negative infinity, 2x minus 3, you bother me, go away. The behavior when you plug in huge numbers or huge numbers that are negative, these two powers take over. And since you are bottom heavy, the denominator is heavy. So that we told you, we asked for the end behavior. That end behavior, this function has a horizontal asymptote or goes off to 0, right? And then what did we tell you? Do you remember what we told you about when the powers are equal? Right? And hopefully, again, that makes sense. I'm plugging in a gazillion. 2x minus 3 doesn't matter, right? Or matters so insignificantly, I can't even tell what it's doing. If you take a gazillion here and cube it, a gazillion here and cube it, a gazillion cubed divided by a gazillion cubed is 1, and you are left with 5 halves times 1, which is 5 halves. You've just answered a limit to infinity question, right? And look at me cheat writing 2 questions in 1, which is so nice with rational functions. If rational functions level off, if they do, they level off to the same number on both sides. They don't like do this. If it's a rational function, that's why we love rational functions, right? So if the end behavior goes to 0 or to a number, 5 halves, you have just answered the limit to infinity question. So a vertical asymptote means you have positive or negative infinity as answers to a limit. Slides is a horizontal asymptote. That's asking you a limit to a positive and negative infinity, which is really just end behavior, which means you've answered this in Algebra 2 already. Again, in our live session, we will talk about this graph. The definition of a horizontal asymptote is a limit to infinity, one of the infinities. You can't do two-sided with infinities, right? You can't come at positive infinity from the right and the left because infinity never ends. So by the very matter of fact of where you're going to infinity, going off to positive infinity or negative infinity is only one-sided limits, right? And if you level off on one side or the other side, you have a horizontal asymptote. Horizontal asymptotes are limits to positive and negative infinity with a number as an answer. Okay, so again, wrapping up. End behavior can also be limits, though, that have an infinity as an answer. For example, this, e to the x. You're supposed to know what e to the x looks like. E to the x slides on one side, but swooshes on the other. So as x approaches infinity, I don't have a horizontal asymptote. I have an infinity, right? So that's not a number. But on t'other side, what's the limit as e to the x as you go to negative infinity? That is 0. So we do say that e to the x, which is not a rational function, has a horizontal asymptote, even though the horizontal asymptote's even just on one side. What about this? If you know what the exponential function looks like, then you know what the log function looks like. This behavior also goes off to positive infinity. Now, these two infinities aren't equal, right? E to the x swooshes off and goes to negative infinity very quickly. ln goes to infinity, but very, very slowly. You know how people say there's no dumb questions? Yeah, well, this is a dumb question. Can you see why? There's no graph over there. Some kids will answer this question and say negative infinity. No, hon. I'm asking you, what is the behavior of the function as x approaches negative infinity? There's no graph there. So I guess you could say this doesn't exist, but that's a dumb question. Don't ask me to evaluate the behavior of a function where the function doesn't exist, right? Silly question. Stop. Know your domains. All right, that's it for this content lesson. So there'll be some during the live session. I'll have that picture. We'll talk about that picture a little bit more. If you want to think about it in between, that's great. And there's a homework assignment that you don't have to do. It's not due until Sunday. You do have to do it, just not right away. You don't have to do it till Sunday. Take care. See you later.